Okay. Now, I mean, this is a classic problem, and it's not classic for you because for a lot of you guys, it's probably the first time you've ever seen a problem like this. But you see this kind of problem all the time when you bend corners in, or even you have this and you cut corners out so that they'll fold in. They fold this side up and you get a little box. Can you guys visualize that? The better you can kind of see that in your head, the easier this kind of problem is. But it's the same idea. You cut out a little x squared from each side. So however long this was, if this was 14, this is now 14 minus 2x. I mean, that's why I call it a classic problem. There's a lot of variations, but you end up with the similar expressions, right? Same kind of ideas. And then you want to know what's the maximum volume you can get. How deep of a cut do you want to make to maximize your volume, right? Number 18 is a little less interesting, like I said. 18 says, what's the maximum product for two numbers that add to 26? Sounds funky. So remember, in most of these problems, they tell me something, and then they ask me something. So in this case, what do they tell me?
I have two numbers.
Yeah, they tell me two numbers added to 26. So how do I write that?
X plus y.
X plus y plus 26. I love it. And then they ask me something about what? They ask me about, not the sum, they ask me about the product. They ask me something about the product. They ask me to maximize it, right? So they tell me about the sum. I wrote that down. And they ask me about the product. What would the product look like? X, y. I've already picked my two numbers. My two numbers are x and y. So what's their product? X, y. So that's my product function if you want. Right? So then remember, what did I say the other day? They always tell you something and then they ask you something. I can't do a damn thing with this, too many freaking variables. But what saves me, they told me something, thank God, right? X and Y aren't free to do whatever the hell they want to. What can I do here? Yeah, solve for, so if I subtract X, Y must be 26 minus X. So then I use that information in there. And then it starts looking exactly like the problem we just did. I get this product function. That sounded a little... Plug in there 26 minus x. Distribute, you get something that looks exactly like the thing we just were working with on the last problem, right? 26x minus x squared. How do you find that, guys? Maximum.
Equals 0.
Shortcut.
You don't want to make this thing equal 0. You want to make this thing maximum. And maybe the maximum is 0, but I don't know. Yeah, shortcut. Negative b over 2a. Whenever you want to maximize, minimize quadratic, something that would be a parabola, that would be located at the vertex, period. So this is called optimization problems. You want the highest profit, you want the lowest cost, you want the highest volume, right? You're trying to optimize these things. That's what I want to do. I want to find the vertex. That's going to be the optimum place. That's going to be where the profit is highest, where the cost is lowest, so forth, right? I want to find that vertex. And what's the quickest way to find any vertex? Negative b over 2a. Once you know x, you can figure out y pretty quickly. What would be your guess for what this would be? I think they say... Oh, okay. What would be your guess for the two numbers? Nobody has a guess? 13. 13 and 13. Because one it could be 0 and 26. They add up to be 26. But their product is 0. Well, I would think that would be pretty low. 1 and 25. They add up to be 26. Their product is 25. Okay, that's better. 2 and 24. They add up to be 26. And their product is 48. Okay, that's even better. So when you do the work, you will get 13. So the other number's got to be 13. 13 times 13 is 169. Anything next to that, what's 12 times 14? I don't know, Jeff.
168.
There you go, cool. 168. See, it's less, isn't it? This will be the biggest product. Anything that you take otherwise will be lower than that. That's kind of cool. This relates to if I wanted to set up a rectangle and I wanted the maximum area, the answer will always be a square. Just think about it. That's exactly related to both sides should be the same length. You got it with me? The minute I start putting rivers and shit in there, then it's not going to be a square anymore. I have lost the side. So I'm going to get some kind of rectangle. But if I use up all the sides, the answer is always going to be a square. That's kind of neat. It's exactly related to this. Sides are the same length. Hopefully. Yeah.
Can you make one step also here?
Sure. What's B?
26.
26. What's A?
-1.
Negative 1. Negative 26 divided by negative 2 is 13. There's the 13. So then y is 26 minus that, so it's 13 also. Yeah. Okay. Maybe. Anything else from homework?
Yes.
Okay. One last thing. Maybe.
A2 blue. Section A2. Number 10.
Number 10?
Yes.
Oh, okay.
Yes, I want to ask, which way should we solve this problem? With complete or just factor?
Everybody has this?
No.
Or you need that? So, you good? Okay. So that section says use quadratic formula or factoring, whichever is best. Or whichever is appropriate. That's fine. I need quadratic. No, it was inappropriate. This one, I always use factoring if it's easy to factor.
Yes.
This is easy to factor. Right? Why? People try to force it like this and then it's hard. But it ain't that. What do you always try first for factoring?
Take 2y.
GCF. You can take a 2y out, you're good.
Yes.
You don't have to do it both ways. You just have to do it either way that makes sense.
What about complete square?
Oh, hell no. No. Especially not in this section. So I got to be careful. This is the kind of problem I would not use completing the square for. We learned completing the square on this kind of problem so we could then develop the quadratic formula, which we'll now use in general. If I don't say how to do it, you sure as all hell use quadratic if it doesn't factor, right? So completing the square has uses. It proved the quadratic formula. There's an immediate crazy good use. And then it has other uses beyond that. But I certainly would not use it on this. Because I have a shortcut if I can't factor it, and then I got factoring if I can.
Yeah.
Right? Good. So it doesn't say anything about completing the square, because now you know quadratic formula. That's a shortcut to completing the square. But here I would just factor it. Be done with it. Yeah. Are you good?
Just ask you after class.
Okay.
I just had a
Just
quick
to
question.
know this.
If on the final exam, if we have a problem that's about factoring, but we can't factor it, but it's before we start, the whole quadratic chapter, should we just leave it as no solution and do that after we get to 13.1?
Oh, I see.
If we have
In the homework, you mean? Not on the final.
on the final, yeah.
Well, on the final, there's no sections. It's just wide open.
Oh, so we,
Unless, if I don't say what to use, you use whatever makes the most sense. We did this
Alright,
semester.
so-
Yeah.
Alright, so if we have like an equation on there that we can't factor it out.
Then you use quadratic
Quadratic
formula.
formula.
Oh yeah. Yeah. So everything is in effect for the whole thing unless I state otherwise in the directions.
Oh, okay.
Cool.
Alright.
I like it. Yeah.
45 for 8.2 in the blue book.
Oh, okay. I like it. So we'll do this. I'll take one more question, and then we'll do some new stuff. what's the first step here to solve this?
Equals 0.
Careful now. I could divide by 3. There's not a damn thing wrong with that. Because could 3 be 0? It's kind of silly. You're like, no, Jeff, 3 is 3, man. Right? I cannot divide by y squared, because what could y squared be? It could be 0. Right? Now, in reality, what I would do is I would say one answer is y is 0. You see how y is everywhere? So if y is 0, it's actually what's called the trivial solution. If I make y 0, everything's freaking 0. I get 0 equals 0, it's true. Boring. Let me say y is 0. Then I can divide by it. Then I'm allowed to divide by it. I say y 0 is an answer. Now, assuming y is not 0, let me see what else is an answer. If I assume it's not 0, I can divide by it. But let's not do that. Because not everybody's going to remember that. You can do that. I would first, since I have higher powers than my y, I want to get it equal to 0. So subtract and add. I could have divided by 3 earlier, so you said divide by 3 is a good idea. So divide by 3. Now what can you do with that? Y squared.
Take y.
Take it out. Right? What are you left with?
Y squared minus y, 2y, plus 2y.
So you get one answer is y squared is 0, so y is 0. Plus or minus 0, which is 0. Right? Is that cool? So that's one answer, great. What's wrong with this dude? It's not factorable, and they told you in the instructions this is going to happen. It said factor something out and do it, and then the rest of it, use quadratic formula on it. So now you just have to use quadratic formula. A, B, C. Cool. So that happens a lot also. You'll get parts that work and parts that don't. Oh crap, alright, so I got to use something else. Is that cool? So we've seen the kind of problem before, but normally in the past we were able to factor all the way down. Now that we know quadratic formula, you don't have to be able to. This piece you use quadratic formula to finish it out. Alright, so one more question I think was... No, good, okay. Let's get back to where we were. I think we'd actually worked our way through 14.2.
You already have the new sheet for the homework chemistry, was it?
Yeah, I had put it up on the overhead last time, and I did not bring it with me this time. But let me ask you a couple of questions just to get us back in the swing here. Can you graph this guy's inverse? So Jay, graph this guy's inverse. Oh, cool. I added all this in. Yeah. No, she was asking me for that. You got that the other day, right? Oh, I see. I got you.
So there's no use anyway.
Gotcha. So what do I do to graph the inverse here?
switch it?
Yeah, so if the function goes through -2, -1, the inverse function goes through -1, -2. And before I get too far, how do I know this has an inverse? We don't know how you know shit, Jeff. No, how does anybody know this has an inverse? It passes the horizontal line test, right? The exact same idea. Vertical line test was checking to make sure every x has only one y. Inverse says I have to be able to go both ways. Every output must have come from only one input, so that would be a horizontal line test. The same exact idea. If I say every y must have come from only one thing, then any parabola is automatically off the table. This y, where did it come from? This input and that input. Oh shit, okay, that's not invertible. I can't. If I know the answer, can you tell me where it started? What did I square to get 16?
4.
No, I squared -4. Haha. I'm sorry. You see, that's what I'm saying. I'm saying you can't tell definitively where it came from because there's more than one place it could have come from. Right? So to be a function, every input can only have one output. This is fine for that. Every input only goes to one output. It passes the vertical line test. To be an invertible function, every output must have come from only one input. That's why that would be a horizontal line test. The exact same idea as the vertical. So here, does it pass a horizontal line test? Yes. There's no horizontal line that would go through more than once. It doesn't turn back on itself like that. Just like this would not be a function, would it? Because it turned back on itself. So now I'm just thinking in the other direction. It can't turn back on itself in that direction either. That's why it kind of makes sense. It's a 1-to-1. Every input goes to one output. Every output came from only one input, 1-to-1. Hopefully. So this function, the inverse function, has to go through -1, -2,
3, 0.
3, 0,
4, 3.
and 4, 3. So -1, -2, 3, 0, and 4, 3. You can do it. There you go. And you can see the symmetry. Even though my scale is always a little sucky, the mirror would go right there along the y = x line. Okay, so you can see that. It's kind of nice, kind of neat to see that. And notice also, is this a function, this black line, is that a function? Yes, it's guaranteed to be a function. It passes the vertical line test, right? Let me blow your minds a little bit. If I took this parabola and I inverted it, I flipped it around the y = x line, I would end up with this. Is that a function? No, it doesn't pass the vertical line test. So instead of flipping it, I just don't flip it. I flip my test. I do a horizontal line test. There's a whole other reason why it's a horizontal line test. I could flip it and then do the vertical and say it's not a function, shit. Or you just don't flip the damn thing, you just do a horizontal line test. Do you guys kind of get that? That's why we have a horizontal line test. Okay, there's two reasons. All right. So here's the main reason that right now we need to know about inverse functions. How do I graph? Oh, beautiful. A nice little review. Take a second and graph that. Find a few points. Graph that bad boy. If you weren't here last time, good luck. Make a little XY table. So what's 3 to the negative 2? 1/9, 11. Flip it, square it. 3 to the negative 1.
1/3.
3 to the 0.
1.
3 to the first. 3 squared. Yes, sir.
Where's the y?
This function notation takes the place of y, so I can always put y back in. So this is the same thing saying y equals 3 to the x. Function notation, when it first is introduced, takes the place of y. It's a little bit better than just having a y there. But we understand that the output is always going to be the y coordinate of the point, right? So I don't need to call it y. I just call it g of x. I know the output's going to go there. Is that cool? So you can always replace f of x, h of x, g of x with a y if you need to for right then. And that's exactly how we found inverses. We put a y back in there, and then we switch the x and y, and then solve. So I just kind of approximate 1/9. Negative 2, 1/9 is about right there. 1/3 is about right there. 1, I can do that. 3, and then 9 is way up there. So it comes up here. Shoot. What's this thing again? Asymptote. So it's asymptotic. That's just a cool word to say. Asymptotic. There. It never quite reaches that x-axis. It never goes to 0. So, can you graph the inverse of that? Do it. Does this have an inverse? Good place to start. Does this have an inverse? How do you know? Does that thing we talked about a second ago?
Horizontal line.
Yes, cool. It passes the horizontal line test. So I know it has an inverse. Good thing to check before you do it. So now graph this guy's inverse. So f inverse has got to go through the points 1/9, negative 2, 1/3, negative 1, 1, 0, 3, 1, and 9, 2, right? Just flip the points. Switch the x and the y. So it's got to go through the points 1/9, negative 2, 1/3, negative 1, 1, 0, 3, 1, and then 9, 2. So way the hell up there. So it's got to do this thing. Doesn't go down, it keeps going up. Very slowly. Up. And what's going on here? That's the asymptote. It's kind of nifty. Nifty? If I flip the asymptote over the mirror, it goes right there. That's the asymptote now. Everything about that graph gets flipped over. And again, that's kind of nifty. It is. That's the graph, and there's its inverse, the mirror image. Kind of nice. Here's the really weird thing. We know exactly what function this is. That's 3 to the x. What the hell did we just do? What is that? I don't know what function that is. I know it's g inverse, right? Keep saying F, but too bad for me. I know it's g inverse. But I don't have an expression for it. I don't have a symbol for it yet. Okay, so let me go a little further here with this idea. How would you solve that equation? cube root it, because we know the inverse function, and we have a symbol for it, so I can actually represent it. I would much rather say the answer is the cube root of 7, then I would like to say, well, it's the number that I cubed to get 7. I'd rather just have a symbol, a way to say it quickly, right? So the same way with this. If I have, what's the answer to that equation?
Three.
Squared. X is 2. The answer is 2. You with me? But what do you do to both sides to solve that equation? We don't have a symbol for this. I can't take a square root or something. That's never going to kill. I don't have an inverse for it. I have a picture of an inverse. That's going to do me a lot of good. Right? But it actually does help me. If an input of 9, I just erased my damn thing. But an input of 9 for my inverse would have an output of 2. That's what we just said. That's what you just told me. Right? So now the input is supposed to be this. So just like this, I can write that as the input of the inverse function. Are you with me? A cube has a 7 as an output. So the answer would be a cube root of 7. You see how the output here is the input here? What do I square to get 9? 3. What's the square root of 9? 3. Right? So it's putting this inside. I need to be able to write this not just as 3 to the x equals something. I want to write it as a symbol of x equals that. I want that to be a function in its own right. So we created, if I have x cubed, we created the symbol, the root, to represent the opposite. Right? So the really cool thing is people hate logarithms because they just don't know the question to ask themselves when they see it. What the hell do I mean? I mean this. When I write this down, what's the question that's asking? Why is the answer 3? Because it takes 3 3s. So the question this is asking is, what does it take 3 of to multiply to be this? That's why we're able to do roots, because we know what the question is that from that symbol. We know what the symbol means. So 2 things. We got to come up with a symbol for this, and then we have to really understand what that symbol means, what it's asking us to do. So the symbol we use, this guy here, is log base 3 of x. Why did they choose that? I don't know. They could have chosen a box with a dot in it, but they chose log, right? And it's from the Latin logarithmos, the study of numbers or some weird shit like that. Yeah?
And the g negative 1x, that's the inverse part. The inverse is the g negative 1.
Yep, that's the inverse. So if g is 3 to the x, the inverse is log base 3 of x. So if h is 11 to the x, h inverse is log base 11 of x. Right? In fact, I mean, look at this. What's the base? What's the base? 3. So it kind of makes sense that it ends up in the base. Log base 3x, log base 11x, so forth. Cool. So now we've established a symbol for this. And it could have been anything. If you were alive back then and you were doing math shit, you could have said, let's not make it a log. Let's make it a wavy line. You know, the symbol for log could have been wavy line with a 3 next to it. You know, it could have been any damn thing. But they were having a rough day. And they said, log, let's just go home. Right? I wasn't. That's the real history now. So now watch this. Now here's the second part. We got a symbol. Now we got to know what that symbol really is asking me. So if I write down here, what is log base 3 of 9? You've already answered this question for me. This is asking, what do I raise 3 to get 9? Because look, here's the exact same problem written like that. Those were the same exact problem. What do I raise 3 to get 9? So when you see a logarithm, it's saying, what do I raise this base to get this output? And of course, what do I raise 3 to get 9? The second power. So a logarithm is a power. This is a huge note. Write that down, box it off, little stars. A logarithm is always the power the base needs. So output for a logarithm is always a power. However you want to say that. That's huge, because all the properties of logarithms are the same as the properties of powers. And we know those. So, try this one. What's log base 4 of 64? Careful.
Eight.
So what's the question this is asking?
How many?
What do I raise 4 to get 64? That's what you multiply 4 by.
By 4.
I'm asking, what do you raise 4 to? You raise it to the third power. Or another way to say it is, how many of these have to multiply to get this? 3 of them. Right? So real quick, watch this. You can always rewrite a logarithm. 4 to the third power is 64. You can rewrite a logarithm in exponential form just like that. So over here, how would I write that as a logarithm? Log base what? Base 3. The output is the input. The answer is the power. Bam. It's always harder to go from this to this. To go from log to this is just 3 to the x equals 9. You can just kind of draw your little arrows. Right? Okay, maybe. Do you guys understand what I mean? That's the key thing. I don't think anybody really ever says that. If you understand the question the symbol represents, you can do the problem. And a lot of people, I think, just don't say that. They start doing a lot of examples, but students don't quite catch on. Where's that coming from? It's not difficult. Logarithms are not difficult. Let me show you one that looks like it would be. Log base 3 of 1/9. I love it. You got to square 3 to get 9, and to flip it, it's got to be negative power. So the answer is -2. What do I raise 3 to get 1/9? Well, I got to flip it, so it's got to be negative, and I got to square it to make it 9. So you just got to think backwards. The exact same way you have to think backwards for roots. Roots ask you a backwards question. Logs ask you a backwards question the same way. Okay. So what about this here? Log base 172. What? Careful. Remember what the question is it's asking you. When you first learn logarithms, you really have to state that question in your head before you make it internal. So roots, you don't have to really do that as much anymore. You kind of internalize it. Here, you got to say to yourself, okay, what do I raise 172 to get 1? What power do I need on this to make it 1? 0. 172 to the 0 power is 1. Is that cool? That's the step I think students skip. They feel like they're supposed to be able to do logarithms, and nobody tells them, no, you got to be able to say that question to yourself, and then they're easy. You can do it, Jeff. Roman numerals. Okay. Let's see, what's the last one? What did we do here? Log.
Maybe minus. Minus.
The base can't be negative. It's a good question, though. There's some, there's a lot of, not experimentation. It sounds kind of weird to say that about mathematics, but you start playing with what the base could be, and you start seeing what the outputs come in. Anyway, so in general, it can't be negative. Yeah. And 1 wouldn't make any sense either. Because 1 to any power is 1. So I can only have a 1 input. That would not be very exciting. But log base 5 of what is 1? Rewrite this. How would this look like in exponential form? 5 to the first power.
5.
Answer. Done. Right? So you have to be able to rewrite that in both forms. One form might be more useful than the other. Okay. Oh, here. So do that kind of thing real quick. Rewrite this as a log. Rewrite as exponential.
Log number, power m.
Yeah, that's a pi, right? Yeah. Let's do this one first. This is normally easier to go from log to exponential. Pi to the fourth equals n. That's done. All right. Didn't say solve. It just says rewrite as exponential form. Right. How do I rewrite this as a log? What's the base? A. What's the power? M. So the b has to go there. How do inverse functions relate? One guy's output is the other guy's input. There you go. So you can see it. One guy's input is the other guy's output. I mean, there you go. So you can always write something and then just double check. A to the m equals b. Yes. All right. Just take a second and make sure you get back to what that was. There's a lot of similarities between logs and square roots, but they're definitely not, or just roots. But they're not the same thing. You got to be careful. Okay. This is 14.3 in the white book. I think in the blue book. Here we go. It's about 9.3 in the blue book. Yep. Okay, so I want to do, let's see, yes. I want to get at least one more, if not two more sections done. That sounds doable. So we got this here. Does it make some kind of sense? If this is how many of you guys this is the first time you're working with logarithms? All right. Okay, so just give yourself time. Right, let it sink in. Hopefully, it makes a little sense. And it's really nothing more than what I just said. We have to have some kind of symbol there to represent what it is. I don't want to write the question every damn time. Right? I want to have a symbol like a cube root symbol. We got a cube root symbol. Why don't we have a symbol for log? We do. Unfortunately, they chose this, which sounds more like you're walking through a forest and you stumble over something. But too bad, we just got to deal with it. So if logs are powers, logs are powers. Let me ask you a couple questions here. What's log base A of A to the 7th? This is a funny question because it's too easy, so it seems difficult. This is way too easy. Yeah, 7. So it's two ways this is easy. What do I raise A to get A to the 7th? Well, 7. And another way this is easy is, how are log base A and A to a power related? What are those two functions? What kind of functions are they? Log base A of x and A to the x. Those are inverse functions. So what will they do to each other? Kill each other. So I'm left with 7. You guys with me? So with that in mind, what's this? Now that was simple, right? You with me? Now watch Jeff make it difficult, but oh well, I always have to do this. Look back at that again. What does that represent? What does that represent? What is a log? Power. So what does that represent exactly? The power that does what? Makes what become what? What does this mean? What is this again? What is that? What's the answer? 2. Why? Because 2 is the power I put on 3 to make it 9. So that's the power that I put on 11 to make it 2. So when I put it on 11, I make it 2. That's a whole other reason why the answer is 2. What's the better way to do it? Just kill the opposite functions. I understand. But it's good to kind of realize that by itself represents a power. The power that 11 needs to make 2. So when I put it on 11, I make it 2. That's exactly what the stupid thing does. By definition, right? So maybe. Every time I talk about powers like that, I always remember the movie Labyrinth. You ever seen it? You remember the babe. What babe? Stay with me. Anyway, that was almost Michael Jackson in that role. It was funny. Yeah, that would have been funny.
No, that was funny.
So, if logs are powers, I'm going to keep that up here. If logs are powers, and I've got this, I've got log base A of m plus log base A of n. Okay, now first off, do you think you can add those?
No.
Probably not the way I said it, right? They're not like terms. I'd have to have the exact same, and then a log base A of m plus log base A of m, and then that's 2 log base A of m. I can collect them, right? I can't add these. But there is something I can do, believe it or not. There's one thing, because of the fact that these are powers. When do I add powers?
When you multiply.
When you multiply like bases. What are the bases on each of these? A. So I added the powers. It must have come from when I was multiplying the things. Oh, sure. That's a property of logarithms. Right? When you have a log of a product, it's the sum of the logs. Because what do you do when you multiply things with powers? You add the powers. This is what I meant earlier when I said all the properties of logarithms are exactly the same as the properties of powers, because logs are powers. Right? So what do you think this would have come from? Division. So it would be log base A m over n. Cool. So if I'm subtracting the powers, I must have had the division of the things. Right? That's really what that says. When I'm adding the powers, I must have had a multiplication of the things.
So the cycle is sort of like the before and after sort of thing.
Sort of, yeah. And I could try to show you the proof. The proof is not very illuminating. I always try to show it, and right now I'm like, should I even show it? It never really gets the idea here. The biggest mistake people make is that they give me like log base 2 of 7 minus log base 2 of 9, and they say the answer is log base 2 of 7 over log base 2 of 9. Yay, because you said divide, Jeff. That's what you said. Well, what's wrong with that? I can't have subtraction of two things become division of those two things. That is impossible. I never said that. Subtraction cannot become division. But I could maybe have another way to rewrite the subtraction. That should be written as what?
7 over
Of 7 over 9. Beautiful. I love it. So if I have, go with me for a second. If I have, how do I want to say this? A squared times A cubed. That would be A to the 5th, right? So when I multiply like bases, I add the powers. Right? So, I mean, I almost went into the proof, but I don't want to. I think I'll stay with it. So, what do we have so far? We have the log of a product is the sum of the logs. The log of a quotient is the difference of the logs. Exactly going along with the properties of powers, right? And real quick, before we go to the next property, I want to show you where this comes in handy. What you got, Jeff? I don't know. So if I had log base 5 of 50 minus log base 5 of 2. Can anybody tell me what that is? What power do I raise 5 to make it 50? I have no idea, right? I like that some of you guys are. No. You can guess. It'd be somewhere in between 2 and 3. Anywhere, so I don't know. Because squared is 25 and cubed is 125. It's in between those. And what's log base 5 of 2? I do not have a clue. Right? But how can I rewrite this? Log base 5 of 50 divided by 2. Log base 5 of 25, which is? Careful. 2. It's all about the powers. What power do I need on this to make it this? Yeah. It's not division, it's not rooting, it's something new. It's a brand new function for most of you. So there's one quick application of it. I can't do either piece of this by itself, but together using a property I can do it. So one of the most important properties is this one. I want to write this. Make it m to the x. How to rewrite this? Right, log base a of m to the x. So what is this really? How could I rewrite this? Expand this out? Couldn't I write this as log base a of m times m x times? Isn't that what that means? Is that cool? No? That's not what it means? Oh, shit. What's m to the x power mean? I've got x m's multiplying, right? If this is m cubed, couldn't I write it as m times m times m? Right, so I didn't want to be that specific. It's supposed to be a property. It's supposed to not care what's up there. So I can do that. Write m x times. And then I can use the first property. I got log base a of m times m times m. So it's log base a of m plus log base a of m plus log base a of m. Oh, crap. And how many times am I going to write that out? X times. So how many log base a of m's do I have? X. So I got x log base a of m's. What do I do when I raise something with the power to a power? What do I do with the powers when I do this? What do I do with those powers? Multiply. So look what it's saying. That's the power I'm raising this to. So I multiply that by this guy's power. Logarithm is a power, right? So when I raise something with a power to a power, I multiply the powers. A logarithm is a power. Every single property of logs is a corresponding property of powers. This is the most important property. Okay, Jeff. Whatever you say, man. But the reason that is, and just to jump ahead a little bit, is we eventually want to be able to solve this kind of an equation. And the biggest problem with trying to solve that equation is, where is my x? Where's my x? In the numerator, right? I have to somehow get it down. Normally, if it was on the bottom, I would multiply it up. If it was inside of a radical, I would square. If it was, I know how to unstick it out of all these different places. But how the hell do I unstick it there? I take the log of both sides. Because look what it would do. It would take that power down. So if I took some kind of a log, I don't care what kind of a log, of both sides, I could take that down. That's the property. So now I've freed my x up. And then how do I solve for x? I divide by whatever the hell that is, right? It's a little preview. I just want to show you why that's the most important property. That's the one that, well, and I think I might have said this before, but what you do in math is you learn a new function, you learn its inverse, so you can solve equations, right? Yeah, I did say that. There's an example of it. We learned a new function, we learned its inverse, right? 5 to the x inverse is log base 5. I can now solve equations with that function in it. Oh, well, that's nice. Blah, 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 blah. Okay. Let's see. Let's try a couple of these problems out using these properties. A lot of times in math, we desperately want to get things together. You know, it's kind of satisfying to have this ugly, huge thing and just kind of consolidate it into one little thing. So that's exactly what's going to happen here. I can use the properties to rewrite this thing as one log. Now, do I have a property about 3 logs minus 2 logs? I don't have any damn property. I have a property that log minus log, I know what to do. Now I've got Ren and Stimpy in my head. So we get that reference? Everybody loves it, log? No?
Yeah.
Is it too old? A few of you guys, okay. The rest of you are like, just shut up, Jess, just do math. So my point there, I don't know if you guys get my point. I don't have any property that tells me what to do with 3 logs minus 2 logs. So these coefficients are in my way. But what can I do, we just talked about, in reverse? Put it back up. That can go back up as a power. Math can go both ways. It doesn't care, right? Don't judge it. So up goes the 3. Here, you know, the 2 can go up. And there, the 1/3 can go up. Now I have properties about subtraction of logs. I have properties about additional logs. I can do it. I got those coefficients out of the way. What is log m of this minus log m of that? Log m. W cubed over a squared. Right? You subtract powers when you divide the things. With me? It's kind of nice that these properties of this brand new function are exactly properties we already know. Don't have to memorize any new shit, right? I'm subtracting the powers. I must have been dividing the stuff. And then finally, what can I do with this guy? The log of this plus the log of that. Multiply. So it just ends up here. Bam. Do you guys see that? So that's what it means. Rewrite as a single log. There's a single log with a whole bunch of crap inside. Now, of course, they could ask you to do the opposite. They can say, start here and break it up. Again, like I said earlier, math goes both ways. It doesn't care. So I can start here and then break it back up. Right? So depending on what you're doing, you want to go one way or the other. Okay, cool. Yeah, let's see. Might be enough. Let me give you something to try here. And then we'll do a little preview and then we'll call it a day. Let's see. You should try to do what I just said. Try to break this up. Break up into log parts. That sounds weird. Log. Just to help you out a little bit, since logs are all about the powers, what's sort of written wrong? What's written a little incorrectly for what do I want to do? Yeah, the root. I'd rather write square root of m as m to the square root is the same as what power? 1/2. Because when you take a square root, what do you do to a number? You break it in half, right? So rewrite that as m to the 1/2 and then attack it the opposite of what we just did here. Start tearing it apart. See if that left a little a to the 4th power. Where'd he go? So in these two, aren't they multiplying? So the product should become to yeah. So it's only the guys on the bottom should end up being the minus, yeah. So you first rewrite that. Just save myself some time. The only one that's going to end up subtracting is the 8 to the 4th part. That's the only one that's dividing, right? So you kind of go straight to this log base b w squared plus, because these are multiplying, log base b m to the 1/2 minus, because that's dividing, log base b of a to the 4th. So that's the first way you can kind of break that up is across the multiplications and divisions. Yeah, exactly. Now you take the exponents down. 2 log b w plus 1/2 log b m minus 4 log b a. So we did the exact reverse of what we did here. And in something like calculus, you would definitely break this thing up into that because it's easier to apply calculus stuff to little pieces like that than it is to this big ugly thing. So that's one place where you want to go this way. Yeah.
For the test, if we do just the second, like the last step, that one.
Oh, you don't do this step?
That one, yeah.
You just go here?
Yes.
That's awesome.
Oh.
That's fine.
Okay.
I was just doing more just to show what's going on. Yeah.
What if you have the 4 or the 1/2?
Yeah. The M before the M.
Yeah.
Oh, as long as it's minus.
Uh-huh.
If you have these switched, it's fine. I mean, of course, any reordering of this is perfectly fine because we know we can do that any order we want to. Cool. Okay. So the last thing. Look at your calculators. Do you have your calculators with you? Do you see anything on that calculator related to what we're talking about right now? Log. I see a log on there, right? Maybe, depending on what kind of calculator you have. If you have a power button, where would you be? There it is. Whoa, right in the middle of the top. See it? Cool. So everybody, do you see a log button? Right? Do you see how it didn't have a base on it? So when I write this, I know what that means. What does that mean? Square root. I don't have to put a little 2 there, do I? Why not? Because math people were lazy. We just said, okay, everybody knows this is square. I'm not going to take the time to write it. So the one log that shows up the most, and this is the only time I'm going to write like this, is log base 10. That's the one we use the most in real life. So we live in California. I used to teach in Virginia, so this had very little relevance there. But here we live with earthquakes, a lot more than we did in Virginia. So we all know about the Richter scale. Richter scale is a logarithmic scale. It's based on log base 10. So every time you go up by 1, you actually go up by a power of 10 in magnitude. That's why you change the number a little bit. Was it a 4.2 or a 4.3? Like, who cares? Well, actually, it makes a kind of a big difference in the power of the earthquake. You guys semi with me? And when you go to a rock concert or something, you listen to the music, and it's pretty damn loud, right? You use, what do you use to measure strength of sound? Decibels. And they're based off of log base 10. So it's the same way that we had this symbol, we said, why write the 2? Same thing with it. We don't write the 10. This is called the common logarithm. And yes, there's a stupid math joke about Abraham Lincoln in a log cabin. So there's a lot of freaking, like this joke, right? You guys ever noticed? So this, on your calculator, when you see log, do you see how right next to it, like above it, it says 10 to the x? Those are inverse functions, so they put those together. So help me out. Try to figure out what's log of 1047. See if we can all use that log button. Unless you have that kind of calculator, no. I don't think you have do you have a log on there?
Yeah.
You do?
No, not here.
Not there, yeah. But you have another one with, okay, good. Yeah, this should be about 3 something, so you're getting 3.02. And how do I know it's going to be about 3 something? Because what do I raise 10 to get 1,000? To the third power, right? So a little bit more than 1,000 should be a little bit more than 3. Cool. So this is an example. If I had log of 156, what would that be? 2.19? So you see a magnitude 2.19 versus a magnitude 3.02 is actually a difference of almost a factor of 10 in power. So this is what I'm talking about with the Richter scale thing. Okay. Cool. So if I want to do something on my calculator like this, log base 7 of 82.9. Can you do that? I want to see if anyone starts to try. No, you don't have a log base 7 button, right? To program that in your calculator, it would actually have to be kind of a thick dude with a lot of batteries and a big memory space, right? It would take a lot to program that sucker to do all these different logarithms. I think some of the HPs with stack technology, they can do logs of all these bases. I don't know, but let's not go there. There's got to be another way to do this based off of what we actually have in a calculator. So this is the last thing we're doing today, just in case you're getting antsy. What is this? What's the answer? I don't know. What's X? Cool. Now, I like that. How could I rewrite this as an exponential equation?
7.
Yeah, 7 to the X. Because I get 2.9. Now, what did I say earlier? I can apply, how do I get that X down to solve this again? I can either go right back to where we were, which is not a good idea, because that was bad.
Log.
But I apply a log I actually have on my calculator. And the only log we know about right now, we have 2 on there actually, but the only one we know right now is log. Base 10, but we don't have to write that. So if I take log of both sides, what's good on this side that happens? Why did we do that? The X comes down. And then how do I get X by itself? Divide. So watch this. This is kind of neat. So X, what was X? X was this thing. So log 7 of 82.9 can be rewritten as log of 82.9 over log 7. You can always rewrite any logarithm like this. And look at this. The base ends up on the bottom. Base, bottom. Right? Easy to remember. I must be telling you, you're going to have to memorize this. So somebody give me a guess as to what this would be? It's in between what and what? What do I raise 7 to get this? 7 squared is 49. 7 cubed is 343. So it's in between there. So it's going to be in between 2 and 3. So somebody help me out. What's log 82.9? And be careful. If your calculator does a parenthesis, you better close that bad boy. Divided by log of 7.
2.27.
That sounds better. It's definitely higher than 2. You got to be careful. Now again, did yours open a parenthesis?
Yeah.
Did you if you don't close it, do you see what happens? It sucks all the stuff inside that first log. You have to close it so you tell me I'm done with that first log. It's sort of like Microsoft Word. I hate that. It opens. Do you need a parenthesis? No, I don't. You stupid thing. But we just have to remember to close it if we really didn't want it. So close it. Log 7. You should get, what is it, 2.27? That sounds right. In between 2 and 3, closer to 2, because that's closer to 49. Got to get a feel for it. You guys kind of with me? This little thing here is called the change of base formula. So you can always do that. If I have log base pi of square root of 7, how can I write that differently? What goes on the bottom? Remember? What went on the bottom? The base. So this will be log pi. What goes on the top? The thing. Log square root of 7. So you can actually do that in your calculator, see what it would be. I'm thinking it would be less than 1. I don't know. You guys want to do that?
Excuse me.
Yeah.
The last step, I don't understand. Yes. Divide log.
Yeah, so this is the overall result. Here's my work, right?
Yes.
So divide by log 7 to get the x by itself. So I get x equals log this over log this. But what was x? This. So log 7, 82.9 is equal to that log over that log. The base all goes on the bottom. That's a way to remember that. Okay. And that's in section 14.5 in the white book. I can't remember. The blue book, blah, 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 blah. Here, 9.6 in the blue book. Okay. So tomorrow I'll have the quizzes graded. I'll make it, we'll firm up, we'll fill in the gaps and some stuff in the exponential logarithmic section. And I'll have the practice test, because remember the test is next Tuesday. Okay.